Siete tutti pregati di prendere posto, grazie. Study the University of Vice President of Teaching, Research, International Relations, and Technology Transfer, Head of Department, and Rector Andy Gibson. Would you sit down, please? The rector of the University of Siena, Professor Roberto Di Pietra, is going to take the floor.
Ladies and gentlemen, I'm really pleased to open this ceremony of the University of Siena. At the opening of this ceremony, I have the opportunity to extend my greetings and heartfelt thanks to the authority present. A sincere thank to all those who have worked on the organization of this ceremony. Greetings and heartfelt thanks, not merely formality, to our distinguished guests, Professor Yann LeCun, Professor at the University Canon School of Engineering. We are pleased and honored by your participation in this ceremony at the University of Siena. A few days ago, I started to think about this speech, and I started to write it. Yesterday, I asked to ChatGPT to create some element, and I have asked what I could write to introduce the laurea compared to Yann LeCun. In 30 seconds, I had the answer. But believe me, I don't like it. my speech, in my opinion, is better. Firstly, because I would like to start telling you something about the University of Siena. The University of Siena is one of the oldest universities in the world, with nearly 80 centuries of history. The first document dates back to December 26, 1140. We belong to the group of the oldest 10 universities in the world. The place where we are today is built up 1 century after the establishment of the University of Siena. It was in the 13th century, 1343. Our university is inseparably linked to its city and its territories. Yet it has always been a part of an international network of relationships. Its first students in the 13th century were also foreign students of German origin. The University of Siena is an institution characterized by a wide variety of richness of disciplines operating in numerous areas of science and knowledge, from experimental science of economics, law, politics, and social sciences, from medical sciences to literacy, philosophical, historical, and artistic disciplines. The University of Siena boasts numerous excellence in various fields of knowledge, from humanities to history, from life sciences to medicine, from social sciences to engineering. These excellences connect us to the cultural context, the business world, and the productive system, both locally and internationally. In the specific field of engineering disciplines, we have a recent history that has quickly taken root, especially in the field of computer engineering, informatics, and, of course, artificial intelligence. This establishment has not only impacted our study programs, bachelor's, master of science, and PhD programs, but also research activities and the dissemination of knowledge, thereby creating numerous relationships between with the business world. These relationships in the Tuscany region have led to the creation of the company network called Siena, with the contribution of the Monte dei Paschi Siena Foundation. Furthermore, these relationships in the same regional territory will allow us to acquire a supercomputer through the creation of a specific joint venture between the University of Siena and the network of companies, with a total investment of over €1 million. The honorary degree we have the pleasure of conferring this morning perfectly aligns with his research field that characterizes the University of Siena and concerns the field of artificial intelligence. The honorary degree constitutes recognition of a journey, the maturation of experience and knowledge, and many achievements made available to the institutional scientific community. The honorary degree is both an act of recognition and a form of gratitude for the contribution made to science and knowledge. This decision was made by the University of Siena when this year we decided to confer the degree in artificial intelligence and automation engineering to Professor Yann LeCun, confirmed by the Ministry of University Research last month of April. We have made this decision because, like all the universities in this country, our institution is a place of science, knowledge, and culture, and it must remain so in the face of any attempt to legitimize pseudosciences and anti-sciences belief. Today, the University of Siena enriched its alumni association with the new graduates who rightfully became part of our community. Finally, let me invite our guests and all the participants to enjoy our ceremony, and let me thank you all for attending these moments in our university. Thank you so much.
Professor Valerio Vignoli, Head of Department of Information Engineering and Mathematics, is going to take the floor and read the motivation for the University of Siena to confer an honorary degree in Artificial Intelligence and Automation Engineering to Professor Yann LeCun.
Esteemed director, colleagues, distinguished audience present. It's an honor and a pleasure for me to be here today to introduce the award of the laurea honoris causa in artificial intelligence and automation engineering. This award was strongly desired by the Department of Information Engineering and Mathematics for the outstanding scientific profile. A researcher who has given and is giving significant contributions in several research fields, starting from machine learning to computer vision, mobile robotics, computational neurosciences, just to name. In addition to his academic achievements as engineers, we appreciate the attention paid by Professor LeCun on practical applications. From this point of view, I just want to mention his contribution to the field of optical character recognition that we have all experienced personally. The scientific profile of Professor LeCun is evidenced by the numerous recognitions he has received all around the world. Among these recognitions, one stands out, the Turing Award. He received the Turing Award in 2018 together with his colleagues Joshua Bengio and Geoffrey Hinton, for the theoretical and the engineering breakthroughs in the field of deep neural network. The Turing Award, which is also known as the Nobel Prize in Computer Science, recognizes him as one of the most influential researchers in the field of artificial intelligence. Even if in a few minutes, I hope to have effectively outlined the reasons why we are gathered here today to hear this. Before leaving the floor to my colleague, Professor Marco Fori, I just would like to express my sincere hope that this event, along with the remarkable achievement of Professor LeCun, will serve as some inspiration for future generations and all the researchers of my department and of our university.
Professor Marco Gori of Department of Information Engineering and Mathematics is invited to reach the dais for the laudatio.
So, good morning. And first of all, I would like to thank the participants and all research is involved in this workshop on neural symbolic learning, listening, and learning. And the participants also the other parallel workshop that we are going to organize today is a parallel workshop with companies which has been organized by the Siena Artificial Intelligence Foundation. And I want also, of course, to the colleagues from the University of Siena. And we see the professor at the prestigious Grand Institute of Mathematical Science, and is also a chief scientist at Meta. And where his research activity has been providing a crucial contribution to the foundations of the overall field of AI. And that has provided also an impressive impact in companies and society. As previously mentioned by Professor Vignoli, was one of the most distinctive achievements is this Turing Award that is received at there are many other achievements during this time. So the analysis of his contribution that I'm briefly going to present covers the impact of research in complex society, as well as his pioneering role in establishing foundations on neural networks and AI. And this second part is, at least for me, very important, maybe because of my age and maybe because I was starting my activity more or less at the time to which Professor LeCun is an important contribution. So let's start briefly with impacting companies and society. Well, I believe that has elapsed since technologies on large language models have appeared in the web. I think the lives of those of us who work with information have been utterly transformed. Maybe most, perhaps even all, of what we need to do can be nowadays provided by intelligent agents, which are, however, still exposed to dramatic mistakes. Regardless of the position one can mature on the impact that this technology will have in society, we believe that the novelty of generative autonomous mechanisms for language generation, in any case, will have a profound impact on society, education, and geopolitical issues. But the explosion of interest in artificial intelligence, I think, is well beyond recent achievements such as the impact in other fields, including speech, vision, robotics, automatic navigation, has been changing our life. The adoption of artificial intelligence for climate prediction, and especially the impact in medicine and biology, can dramatically contribute to the improvement of the quality of climate. Now, if you count the scientists who have contributed most to this development of AI on the fingers of one hand, I think you cannot exclude Professor LeCun. Spend a fruitful activity at Bell Labs by focusing on neural networks and learning algorithms and providing at the same time, I think, an extraordinary evidence of engineering skills. A remarkable example, which was quickly also mentioned by Professor Vignoli as a kind of research, concerned printed and unwritten text. So the technology, which was based on graph transformer networks, was licensed by specialist providers of advanced systems, such as National Education Register, and it was massively used in the United States. Now, interestingly, the technology behind these systems, for people like me who teach machine learning from years at the university, connect immediately and really might a popular APIST unwritten character recognition database, which is now associated to his name, that is, again, widely used in machine learning courses all over the world. So he has been playing, I think, a primary role in the conception and evolution of large language models and overall of generative AI. Could be have a look at the large language models made, for example, the popular Llama model. And overall, I would say that throughout his career, he has built a very high find reputation for converting ideas into technologies. That's probably one of the most simple way of distinguishing Professor LeCun. Let me now quickly tell you about his pioneering role in the foundation of deep learning and artificial intelligence. By and large, his most impactful contributions came in conjunction with the explosion of deep learning. Is widely recognized as one of the major protagonists behind the discipline, behind the technological impact. He has been one who has proposed deep convolutional neural networks, a class of neural networks that has become likely the most popular architecture in real-world applications. On 2015, together with Jeffrey Hinton of the Oxford Venture, he published on Nature a Siena paper, deep learning. This has been having an impressive influence in artificial intelligence and cognitive science. And among others, it has given rise to a lot of applications in the field of engineering, medicine, and biology. As yet, the paper has received as many as 66,000 citations, Scholar Google citations. Roughly speaking, we are talking about 35 citations per day. The paper discloses the importance of the rich internal representations that are developed in deep neural networks, which is in fact one of the secrets for boosting of performance that we have experimented in the last decade. Now, I like also to mention, the pioneering role that Professor LeCun played on the foundations of neural networks during the so-called first connections. Okay. So the first connection this way is typically marked in the mid-80s. And in order to better grasp the crucial pioneering role that is played in AI, one should be reminded that in the 80s, the connectionist approach was quite marginal. For example, one of the classic textbook in artificial intelligence by Patrick Winston from the Massachusetts Institute of Technology, which at that time was regarded as a sort of Bible for the discipline, reserved a backseat position to the overall field of machine learning. Academic life for scientists who have decided to follow the area of neural networks was not easy at that time, since the field was regarded as peripheral to AI, which was quite peripheral, also in computer science. This minor relevance of the field was mostly perceived in Europe and surely in Italy. On October 1988, I met Yann LeCun at the international conference Connection is in Perspective. One of the first events marked the tomb of what is often referred to as the first connection is way after the entire period following the publication of the seminal book Perceptive by Siena Yann. It was immediately clear to me that despite his young age, Yann was destined to be a protagonist in a new field of research that I too had fallen in love with. He presented a paper entitled Generalization and Network Design Strategies, where the notion of resetting fields and weight sharing that are massively used for deep convolutional networks were already clearly introduced and successfully experimented at that time. When considering their contribution to science, I believe that in addition to the widely accepted biometric indicators, one should be able to identify a few distinctive achievements. There is no doubt that Professor LeCun has had a primary role in both propagation and convolutional neural networks, that have changed the face of AI in the last decades. Professor LeCun began sailing against the wind of discourage the adoption of huge networks because of parameter volatility, which was one of the concerns for years. Its long-standing coherent studies in promotion of the connections approach, the intuition on the role of specific architecture, the pioneering role adopted in propagation and promotion in conjunction with deep neural networks of huge dimensions are the clear sign of his long-term vision and strong foundational scalability. However, his research path is also and maybe primarily characterized by his extraordinary ability in the engineering of large-scale systems, which is in fact one of the major reasons why the field of artificial intelligence is so popular nowadays. He recently proposed a path towards autonomous machine intelligence, where machines learn more like animals and humans, can reason and plan, and are driven by intrinsic objectives rather than by hardwired program, external supervision, or external reward. These studies arise from his claim that scaling up on neural architectures, like in current large language models, is not enough for capturing many interesting and subtle aspects of human intelligence. This path on autonomous machine intelligence surely intersect the research interest of many participants to the workshop on neural symbolic learning and reasoning, which is about to start. So, like other top-level scientists in the history of science, I think Professor LeCun began his career sailing against the wind, against the mainstream, but ultimately strongly contributed to land in the current exciting territory of AI. In conclusion, I turn to you, Yann, to express my gratitude for having accepted our invitation to confer upon you this valuable honorem. We are enthusiastic and eagerly looking forward to follow your relationship studies.
Yann LeCun to reach the dais and deliver his dissertation entitled The Present and Future of Artificial Intelligence.
Thank you very much. Very little honor for me to be here among you. I was anticipating, but that's okay. It's the emotion. So thank you so much for this very fact that you and Marco know each other for 35 years now. This is me. This is everyone here again. It's a huge honor. Real pleasure to be here. It's a beautiful site. And I'm going to tell you a little bit about the present and the future of AI as I see it. And perhaps kind of thought it has the future of AI. Okay, so today AI means machine learning. And if there is something that I think is, as Marco expressed, that has defined my career, it's the idea that building intelligent systems, it's very hard to just write it from scratch, write a program that is intelligent. What you can do is imitate to some extent, get inspiration from biology and get machines to make themselves intelligent through learning and observe biology. Every biological system that has a brain is capable of learning. In fact, even a lot of organisms that don't have a brain are capable of learning adaptation, but really what characterizes biology is the ability to learn that. So perhaps because I did not consider myself smart enough to design an AI system from scratch, I decided that AI systems should design themselves. And started working on machine learning. At the time, in the early 1980s, actually, that machine learning did not actually exist as a field, and was viewed as it. In fact, most of the efforts of machine learning were not viewed as part of AI, viewed as part of statistical recognition, or additive filters, or these fields of engineering, but they had disappeared as a kind of approach to AI in the late 60s. And so this was a very lonely time for a few years until the late 80s when interest in neural net was revived. But really today, AI is machine learning. And there's really three paradigms of machine learning that exist today that are being used, practice or just research. One type of learning is reinforcement learning. And reinforcement learning, you put a simulated system in a situation, and the way the machine learns is by trial and error. It tries something, and then gets an indication from the environment or from the teacher as to whether the output it produced was good or bad. If the number of outputs that are possible is very large, this process is extremely slow. People thought at first that reinforcement learning was a good model of biological learning, but we realize now that it's not. At least it's incomplete because it's extremely efficient. So it's useful for games, because in games we can get a machine to play millions of games against itself, essentially. But in real life, trying to do lots of it's too slow. The second type of learning, which by far was the main workhorse of AI until recently, or machine learning for the last 10 years perhaps, is called supervised learning. So supervised learning, this is what has been used for training a machine to recognize keys, for example, or translate from one language to another, or for speech recognition. And there you tell the machine what the correct answer is. You wait for the machine to produce an answer. If the answer is correct, nothing, it's correct. Tell the machine, here is the correct answer. Modify your internal structures so that next time the same training example is an answer that is closer to the one we want. That's much more efficient because you're giving more information to the system. And then there's a third learning, which basically has become dominant over the last few years. And you see examples of this in generative AI, but there's other ways as well. That's called self-supervised learning. So something I've been advocating for something like 8 years or so, which is the idea that the system is not trained for any particular task other than capturing the structure of the data that it observes. For example, by predicting the future. Okay, so we'll show the system a piece of a video and ask the system what is going to happen next. Or show a system a piece of text and ask it to predict the words that are coming next. This is the way large language models are trained. So you don't need to have a task, you don't need to label anything. The system learns to kind of represent the internal structure of the data by just predicting it. And it's really taken over the world recently. But it's not about supervised learning first. I really was to say it applies to every academic learning, but it's easier to understand it because it's supervised. So let's say I need to train the system to distinguish images of cars from images of airplanes. What I need to do is connect millions of images of cars and airplanes, and then show an image of the car to the system. Ask it to produce an output. If the output is car, don't do anything. If it says airplane or something else, adjust the knobs on the system represented those actual physical here, so that the output is closer to the work you want. I mean, this is brilliant examples, repeatedly possibly. And in the end, the magic of machine learning is such that the system essentially learns the concept of versus an airplane and is able to recognize versus airplanes, even for examples that it's in. And this works really well for images, but also for speech recognition and translation for augmented verification. Mathematically, the way we represent this problem is the problem of mathematical optimization. So we can represent the distance, and how do we get into mathematical argument? We basically measure how well the system is performing by measuring the distance of the output the system produces with the output that we want. The distance, we over a million of examples, and that is a single value that we call a loss. What we need to do is adjust the internal parameters of the system, the knobs that I was representing on the previous slide, so that we find the value of those parameters that minimizes that loss, so that the system most of the time serves the correct output. And we do this through a very simple algorithm that denotes Newton called gradient descent. So essentially, imagine yourself somewhere in the Italian Alps, and there is fog. You're lost in the mountains, and you're trying to look for the valley, for the village. There's fog, you can't see anything around. So what you do is you turn around, and you figure out which way goes downhill, and you take a step downhill, and you keep taking steps downhill until you reach the valley. That assumes a very smooth landscape, which of course is unlikely to be the case here, but here we make that assumption. So the question now becomes, how do we compute this direction, this descent? And that's where the backpropagation algorithm comes in. So what do we put in that box? What are those parameters are we going to adjust? So that's when we got inspiration from biology. This is an inspiration that goes back to the 1950s. In fact, perhaps even to the 40s. The idea that intelligence is an emergent phenomenon in the brain due to the interaction between a very, very large number of very simple elements. The neurons. So the neurons in the brain, if you simplify the function of them, basically compute a very simple function, basically a weighted average of the inputs, or weighted sum of their inputs, and then compare that weighted average to the threshold. Is larger than the threshold, then the neuron gets activated. It's deactivated. Mathematically, it's very simple. Basically, you just have products and additions, right? So take a bunch of other neurons, compute their distance with weights that connect to another. Then compare that weighted sum to the threshold. It's above the threshold, and with the weighted sum is below the threshold at 0. Very, very simple. The only operations you need for this are multiplication, addition, that's it. If you can do billions and billions of that per second, or trillions of that per second, you can run very much movement really fast. And that's basically what a movement is. So it's called deep learning because you build those systems by stacking multiple layers of those components. And those systems may have billions, hundreds of billions, and starting to get into the trillions of those adjustable parameters, which are the weights that connect to those components. So the way this works is you put an input to the output of the network, tell you the output is supposed to produce, and then figure out in which way and by how much to adjust the parameters in the system, the weights that connect each of the neurons, so that the output is closer to the weight. And that's done with the backpropagation algorithm. Ignore the components. They're basically a transcription of something invented by Leibniz order with Newton or chain rule. It's basically, how you create a derivative of a function of a function. It's very simple. So nothing very sophisticated in terms of mathematics, but extremely powerful when you apply it more. And basically, the idea is that propagate signals backwards in the network to indicate in which direction and by how much to adjust each parameter in the system so that the output is constant and the reverse function is communicated. Okay, so then the next question is how do you organize the tools so you connect them with each other so that the system can usefully solve a problem, like let's say image recognition, in this case, image recognition. And that's where the idea of convolutional platform comes in. So this is something I worked on in the late 1980s. And we started working on it then. And basically, the architecture of how the convolutional net is organized is inspired by the structure of the visual cortex in mammals. Mammals in any animal that has vision, neurons in the visual cortex were connected to a small area in the visual field and detect very simple. Okay, here we go. On the input. And that motif detection is replicated everywhere. That's mathematically that's what correlation operation, which is where networks. And those have been extremely successful, back in the late 80s, early 90s for recognizing handwritten digits. We did not apply them to anything else because we just didn't have any data that was credible on the computers, not very powerful at this time. And so we could recognize digits, we could recognize multiple digits. This is an example of one of those systems that was applied. And then the field lost interest in this kind of technique in the mid-90s. And for almost 10 years, most people dismissed neural nets as being useless, interesting, curiosity perhaps, but not really something that should be studied seriously. And it's because partly the theory to explain how neural nets function was very difficult. Neural nets are very, very complex objects, and any kind of theory can work. It's only sort of an approximate representation. So people dismissed it because they could not write a theory for it. Whereas other machine learning algorithms were simple to understand and mechanically. But what happened in the meantime is that around 2012, my colleague Jeff Hinton and his students started implementing convolutional nets on GPUs, the same processors that I used to rapid rendering, which was starting to be very popular. And those systems are, those cards are designed to perform multiplication and addition as an extremely good thing. So they were really appropriate for nets, and they were really cheap because they were designed for gamers, essentially. So they implemented convolutional nets for this and got incredibly good results on the standard benchmark ImageNet that was in 2012. And this kind of revolutionized the field of computer vision and any things like driving assistance systems for cars. Every car in Europe nowadays was called an AEBS, Automatic Emergency Braking System, which means detect obstacles and cause the car to automatically brake collisions. Those use convolutional nets. 80% of the market is dominated by a company called Mobileye, which is an Israeli company, and then various other players. People use convolutional nets. So this thing, it reduces collisions by 40% of stage lives. It's made enormous amount of progress. Enormous amount of progress. It's the demo that was get by my colleagues at Meta a few years ago that shows that those systems can not only detect and classify them, but also detect human figures and identify their pose. Label the also label every object and every region in the image with the category of the object belongs to. This is called instance segmentation or panoptic computer vision. So the performance of the system is incredible nowadays. This is not to say that computer vision is a completely solved problem, but really the performance, if you can have enough data, is incredible. And this is open source, it's called Detectron 2. It's really very good. This has caused a lot of progress also in things like medical imaging. So this is some work by some of my colleagues at NYU in the radiology department, part of the medical school, where they use self-supervised learning in combination with other things and convolutional nets to things like detect tumors in membranes. Other work in collaboration, the collaboration between NWA radiology departments and ETA, the Fundamental AI Research Group, which basically uses deep learning for restoring the quality of MRI images. So basically, those systems produce very high quality images, MRI images, with 1/4 the time that it takes normally to collect the data. So instead of having to lie down in a noisy heavy magnet for 40 minutes, that can be reduced down to about 10 minutes with the same quality. That's because of the properties that we can use in the AI system to restore the quality of images. There's a lot of applications of convolutional nets and other deep learning techniques in neuroscience, in science in general, but science in particular. Convolutional nets now are the sort of dominant model that neuroscientists and psychologists use to explain how the visual system works. There's similar efforts to basically use the deep learning systems that have been trained on language to try to explain how the human brain understands language, but that doesn't work really as well, which seems to indicate that the current models that we have for language understanding not reflect the way that the brain understands and produces language. As I said, lots of applications of deep learning in science, particularly in quantum physics, high energy physics, in astrophysics, in chemistry, material science in particular. Just one example of a project that was started a few years ago by my colleagues at Meta. It's called the Open Catalyst Project. And the idea there is that we need to solve climate change. And one possible approach to solve climate change is to solve the energy storage problem. If we're able to store electrical energy, we could cover a small desert with solar panels and just produce hydrogen instead from water by separating hydrogen from oxygen. And the problem with this is that processes that are known to do this are either scalable or inefficient. But they're not both scalable and efficient. And when they are efficient, use utilities like platinum, and that's not scalable, it's too expensive. And the ones that are scalable are not efficient. So the goal of this is to use AI to discover new compounds, new catalysts that might facilitate the electrolysis of wire. But at the same time, are scalable, use common chemicals. And the data is open, so the data basically is generated by doing DFT simulation very large scale, a supercomputer at Meta, distributing the data and asking scientists around the world, can you train an AI system to extrapolate that data and basically invent new compounds that could help with that. So this is an ongoing project, but very risky, but very interesting. And as I said, deep learning protects lives in the environment at the moment. It's used for all kinds of applications in transportation, etc. Okay, let me switch gear a little bit. So I talked about those three paradigms of learning: reinforcement learning, supervised learning, and self-supervised learning. And I'm going to focus on self-supervised learning now because this is really the future. It's the present as well. It's really has revolutionized AI or machine learning in the last 5 years or so, 5 to 7 years. And if we want to find some sort of analogy or metaphor of learning or machine learning with this beautiful chocolate cake here, we could think of self-supervised really representing the bottom of the cake. This is really where most of learning takes place. And then to learn a particular skill, you can learn in supervised mode. That would be like the icing on the cake, a small piece of the cake, important but small. And then reinforcement learning is just for kind of final fine-tuning. And that's a bit like the cherry on the cake in terms of relative importance of the two paradigm. And so one has to accept the fact that machine learning really sucks today. You have to pardon my French. Compared to humans and animals, our machines today really don't run very well or very fast. As Marco was saying here, things like large language models make very simple mistakes. They hallucinate. They produce bad speeches. When we compare this with humans and animals can learn new tasks really quickly with very few trials. We understand how the world works. Animals do as well. Humans and animals have what we call common sense, and current machines don't do. Okay, so self-supervision is really what has taken over the world. I can explain a little bit what it is. Let's say we have a piece of video, we show the initial segment of the machine, we ask it to predict what's going to happen next, and then we reveal what happens next. And we hope the machine will adjust itself to do a good job by predicting what happens next. And when I say what happens next, it's not necessarily predicting the future, it could be predicting the left half from the right half, or the halves from the present. It doesn't really matter. In fact, the way it's used in the context of natural language processing is the following, or the way it's used for a lot is the following. You take a piece of text, you corrupt it by removing some of the words, replace those words by a blank marker, mask, essentially. Then you take this corrupted text and you run it through a very large neural net, and you train this neural net to predict the words that are missing. In the process of doing so, the system learns an internal representation of text that integrates meaning, syntax, grammar, just everything. And so you can use the internal representation of the text learned by the system as input to a subsequent task like translation, hate speech detection, summarization, anything you want. And this works amazingly well. It's called denoising autoencoder. It's an old idea. If you combine this with a particular architecture of neural nets and transformers, which you can think of as a different family of convolutional nets, there's two big families of neural nets nowadays, convolutional nets and transformers, and very often they're combined actually. Then you can train systems to translate very, very easily. By basically taking two sentences that are translations of each other and masking different parts of those two sentences into transformers. You can train those systems to produce dialogue. So this idea that you can talk to a dialogue system is very old. Pascal actually has been working on this for a while. So Pascal Fong here, Professor Pascal Fong from University of Science and Technology here today. Dialogue system is an old topic, but it's made a lot of progress in recent years, partly because of self-supervised learning applied to text. One particular application of this is for dialogue system. This is actually several years old. It's a system put together by my colleagues called multimodal Mandela. It's a dialogue system that actually understands images. We can comment and make up stories about images. So this is years before ChatGPT. So another example here is a system called Low Version Behind. It's a system again put together by some of my colleagues at Meta that can translate 200 languages quickly in any direction. And it's the magic of it is that it's trained. You don't need to have parallel text to train that system between all the 4,000, 40,000 different directions. In fact, the system has been trained with only data that only represents 2,400 or 2,500 of those directions. And yet the system can translate from any language. With those are the 200 languages that it studies. Actually, several of those are spoken. Not just Italian. There's some idioms where yeah, it's idiom. So 200 languages represent actually a pretty wide range. But it's right here all the several hundred, 700 big languages that are spoken around all from thousands of dialects. So this works really well also for speech recognition. We can now create really good language speech recognition systems something on the order of 10 minutes for transcribed speech in any language. And that allows to fulfill the desire that also was expressed in autonomous speaking, which is that you can now have speech recognition systems that work with very rare languages for which you don't data. In fact, my colleagues put out a system recently that can recognize speech in 1,100 languages. It's a single system, it understands 11 languages, or at least can transcribe them into text. So that's pretty amazing. Similar techniques, this self-supervised learning technique, instead of being applied to text, has been applied to DNA sequences. So we replace the words by, amino acids, essentially. And those systems are able to learn representations of biological structure that captures a lot of the complexity around it. And so now we can use those systems to predict the conformation of proteins, which is sort of a major advance. So two major groups working on this. One, at DeepMind, they produce a system called AlphaFold, AlphaFold2, which can be used by millions of researchers around the world. Another system produced by some of my colleagues, or no former colleagues, called ESNFold and ESNFold2, which can predict, again, the conformation of protein, and also can be used for designing new proteins. So drug design is going to go through a revolution over the next few years, because we can now okay, actually, it's another one. Thank you so much. We can now design a sequence of amino acids so that it will take a particular shape and then bind to a particular location in the cell, for example, and then have a particular function. So this is likely to revolutionize medicine in many ways. My colleagues put together this database of 650 million proteins that are predicted to be structured. This is used again by thousands of researchers. So open source is free. Okay, so this is the present. So we've been talking about generative AI for months at least in the public. Of course, the research has been years, so for us it's really not. And here is how progressive LLMs work. We train them as you take a piece of text, mask the last word, and you train some gigantic neural net to predict the last word in that text. And that window of text is a few thousand words, which are subword units. And once the system has been trained, this may be a system with billions of parameters, or just billions. When the system has been trained, you can use it to just produce text, because it knows how to predict the next word, but produce a piece of text. So you write a piece of text, and then ask it to predict the next word. And then you inject that next word into the input, and ask it to predict the next word. Then inject that to the input, and then keep going. It's called autoregressive prediction. It's an old concept from statistics and signal processing, but it's the same, really the same idea. And those systems are amazing in many ways, in their ability to really understand the content of text and be able to answer questions. But in many ways, they make various mistakes, and that's because they don't have any experience with this world. They only train text, and most of human knowledge actually has nothing to do with language. It has to do with our experience of the physical world. And so those systems are extremely limited in their intelligence. And nobody knows about ChatGPT because it's a product. It's been one of the prototype systems that have been produced for years, including so many years before that, before. So they don't have anything like human intelligence. To get them to work, you have to train them on something on the order of 1 to 2 trillion words of token, again, subword units. That's basically the entire internet, the entire public internet. To read this quantity of text for a person reading 8 hours a day at average speed would require 22,000 years. Babies, children, young children, learn language, a tiny amount of exposure to language. And they are much smarter than any of those systems. They can't pass the bar exam because they haven't read all the text that's relevant. But in terms of raw intelligence, they're much smarter than any of those systems. Because we're nowhere near human level intelligence today. lesson. And those systems can hallucinate. So my colleagues made a tool copy. They trained a large language model and say, did you know that Yann LeCun dropped a rap album last year? We listened to it, and here is what we thought. And then they let the system kind of create the rest, right? So the system obliged and wrote a critique by the alleged rap album. Which you can read. It's hallucination, obviously, I don't this at all. It's music, actually, like some more music. I really the jazz, but it's terrible. So it's like it's like the same thing with jazz at one something. They say, yeah, we tried. It didn't work because it's just not enough data on the internet of jazz reviews. And that made me extremely sad. So those are two aggressive LLMs. They're really useful, they're exciting. There's a lot of applications for them that will reach about in the next years. But really, they suck. They're nowhere near human intelligence, and we need to reach that gap. So a lot of people have been fooled by their fluency, right? They think that intelligence because they speak, but really they don't. They have some level of intelligence, but not anywhere close to what we. And so, in fact, I wrote this philosophy paper last year with my colleague Jake Murphy, who's a philosopher, and about the fact that virtual human knowledge is always brings to the physical world. People in various areas have written critiques of them saying they can reason, they can plan. All the systems are capable of doing it, but they don't capable of running. So that's the big question. One of the challenges that I think that we're facing for the next years in AI is to reconcile the ability to reason and plan, which classically AI systems before machine learning were capable of doing. But basically capable of doing, no need to reason, no need to plan. You don't want to do this, but I have an idea. So I'm going to be very towards artificial intelligence. Also, it's not finished research. It's basically my vision for where AI research next 10 years. So the kind of paper that you get to do when you during the work. If you do this while you're a student, people will laugh at you. All the attention you can put inside and split up themselves, which is planned for the future. So it's based around this idea that some sort of motion architecture is architecture is basically the centerpiece of that idea is the idea that we have a modeling world, and intelligent machine should also have some internal net of the world that it can manipulate reason. And I call this objective-driven AI nowadays. Because when I say autonomous machine intelligence, people get scared. They say, well, autonomous, what are you talking about? You mean machines teach themselves and really autonomous? This is scary. So I call it objective-driven. And the basic idea of this is that system has a model that allows it to predict how the world is going to evolve. So that is something and particularly is able to predict what's going to happen as a consequence of its own actions. If you can predict what's going to happen as a consequence of your own actions, then you can plan. Right? So if I want to get a drink, we need to get a glass out there, then we need the caffeine bottle somewhere in the glass, and then probably put the glass here because I know it'd be stable. I would not put it here because the slanted, the glass was still. So I have this mental model that allows me to kind of plan a sequence of actions that will actually result in the result I want, which is a glass of water I can drink. So that's the idea of objective-driven objective. Systems has an objective that it sets itself, and then it infers a sequence of actions that, according to its own will satisfy this objective. So it would be like steps, right? Because an action we can take a second action. I can predict the resulting outcome of those two actions according to my model. and then check whether those things will satisfy the objective. And perhaps I can put some other objectives that guarantee that the system will only do things that are safe, will not do crazy things that will hurt the users, something like this. And one thing that humans and hackers can do also is plan quickly. So let's imagine, for example, I want to move from New York to Paris, and I'm sitting in my NYU office. I do this in Paris, for example. What I do to plan this is that I first represent the situation at a very level of abstraction. You say, well, first I have to take a taxi to go to the airport, or maybe take the subway. I have to go to the airport and catch a plane to Paris. And I don't need to know any of the details about this. I don't need to go to the airport. Okay, so now I have to plan how to go to the airport. I have to get out of the building, hail a taxi on the street, which you can do in New York. How do I get out of the street? I have to stand up from my chair, take the elevator up the stairs, go down the street. How do I get out of my chair? You know, I have to activate my muscles in a particular way. And so we're planning those actions without even thinking about it practically, all the way down to millisecond by millisecond muscle control. And this type of priority planning, no idea how to do this with AI systems at the moment. We don't have any example of this working. The missing piece is the ability to learn arithmetical models that represent the state of the world and can allow the system to predict the consequences of these actions at multiple levels of abstraction. So I'm heading towards the end. So this leads to a new type of architecture for large language models, which I'm not going to move to. But basically, we allow those systems, instead of producing one input to the other, simply like current systems. Those systems will be able to plan their answers and will be able to guarantee that their answers are safe in the input, like observe some guardrails. And we're working on this. I can't give you an example of how it works because it's still very early. So skip ahead a little bit. So one thing that we're working on is model of this type, train the system to run the works. It's a video, and this is using in fact something that is not generative architectures. We call them JEDA, Generative Predictive Architectures. And I don't have time to go into the details of this. Actually, I don't have time at all, I guess. But maybe just give you the gist of it is the basic idea that instead of predicting exactly all the details that are going to happen in the video in the future, you're training the system to predict an abstract representation of what happens in the video. Okay, so for example, if I take the video of this room where I point the camera here, there's no way that the video prediction system can predict all the details of what this half of the room looks like. The clothes everybody is wearing, their age and gender, what the floor looks like, what the painting will look like. There's no way those details can be predicted, but I can predict that there's probably going to be people sitting in chairs. So at a high level of abstraction, I can make that prediction. It's going to be pretty accurate, just not going to have any details. So that's the idea of making predictions in representation space and that allow us to build models, predictive models, particularly in models in which some of those agenda architectures where one of the inputs to the predictor is an action that I choose to take, the system I choose to take. So, so what I'm asking people to do now, I'm used to making recommendations in AI research that are not popular. I don't know which word you use, but I know against the mainstream, if you want. And I'm asking people to basically abandon generative models in favor of those joint embedding architectures. Because although generative models work with text, they don't be abandon realistic modeling because if you use algebra, you can use probability, mathematics probability modeling. And then abandon a couple of the things which are not technical, so they're very popular. So we use this architecture to actually train an image recognition system, and I have more details. But just to give you a gist of how this works, you take an image, you provide it by scanning a piece of it, So it's the same idea as the text. Then you run both images, and then you train the representation. You train the system to predict the representation of the full image from the representation of the partly masked image. And that works really well. The system trained this way across representations of images to the point that you get really performance on several things that are going to be more details again. And then perhaps at the end, this works with you, you're going to be able to integrate this. Even more architectures that are trained in video, here it's work on this, which I'm going to explain over the flashing pictures, which perhaps will allow us to do this picture systems that can reasonably plan and basically make sense perhaps. Okay, so working on these things, you're working with objective-driven systems for dialogue, with the controllable, steerable, safe, and the taking messages that is whatever is false. So my prediction is that it will disappear within a few years. Be replaced by things that are more objective. Because they calculate the going to be made safe, really. We're still missing essential concepts to which like perhaps the minds of those war models that was taking about. And this war model will be used using strategy, general architectures, and then we'll assemble this in those objective-driven architectures in the future. How long is it going to take to reach a level of AI? I mean, years to decades. It's usually there's no question it will happen. There's no question that as we point to the future, we will have machines more intelligent than humans in all domains. Already have machines that are smarter than humans in very developed domains. Eventually, they'll be smarter than us in every domain. Should we feel threatened by this? No, because we all have basically intelligent assistants helping us in our daily lives. And it would be like one of us has a staff of people working for us that are smarter than us, which is the ideal situation. As the business taking political leader, the best thing you can do is have people who are smarter than you. You shouldn't feel threatened by them. It's exactly that, actually. So this is going to amplify human intelligence. And basically, perhaps cause a new renaissance. Italy is famous for basically it started a renaissance for 30 arts and music and cuisine. Cuisine is the Roman side of the Italian cuisine. Architecture. So all of this was enabled by the invention of the materials, disseminated knowledge. AI is going to be the main tool for disseminating knowledge and for people to acquire knowledge. AI platforms are going to be a repository of all new knowledge that all use access. So I think it is going to cause a new renaissance for humanity, perhaps similar to the previous renaissance, or the enlightened people. So it's a very positive, optimistic view of AI, very different from the pictures that sometimes it's painted in the press by some of my colleagues. The dangers, they are dangerous, those dangers are similar to the dangers of project. This is very difficult to build objects that are safe. It's going to be difficult to build AI systems that are safe and operational. It's an engineering movement. So, once we take this, but I think the future is a point that as Yann made in the keynote this morning. In the future, because AI systems need to be open source. They need to be fine-tuned through crowdsourcing language like Wikipedia. And this is incompatible with any recommendations. If you think AI systems are dangerous, we need to be regulated and ban AI that necessary resource. This is, in my opinion, treating all subsidiary. And what I found in the discussion with political leaders in our cities is that the US is much more committed to regulate AI than some European countries, particularly consequences against revolution developer. Which is the current government very much in favor of taking advantage of farmers for economic development. Thank you very much.
Artificial Intelligence and Automation Engineering to Professor Yann LeCun.
Professor Yann LeCun, per l'autorità conferita dalla legge, la proclama dottore magistrale ad honorem in Artificial Intelligence and Automation Engineering, Siena 3 luglio 2023.
Authorities, guests, and people present. The ceremony for the conference of an honorary degree to Professor Yann LeCun is going to end. We are honored to have him in our academic community. Have a nice day.